Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to have Nikhil Bansal here at Microsoft Research. Nikhil is a professor at Technical University Eindhoven. Before that, he was a research and manager at IBM Research. Nikhil works on various types of algorithms, online algorithms, approximation algorithms, and today he will tell us about the number of matroids.
Hey, thank you, Kostya, and thanks for inviting me. Yeah, so I'll talk about this work on the number of matroids, and it's joint work with Rudi Pendavingh, who's a colleague at TU Eindhoven, and a master's student, Jorn van der Poel. Okay, so probably most of you know what matroids are, have used them extensively, but and these are like central objects in optimization. And one nice thing about them is, they combine like graph theory and linear algebra together. But just to remind you, so matroid is basically a set collection, So you have a universe of elements, let's say 1 through n, and there is a collection of subsets of U, which we'll call as independent sets, which satisfies very basic axioms. So the first axiom is that these sets are subset closed. So if I is independent, that every subset of I is also independent. And a more interesting property is what's called the extension property. So if you have two independent sets, say I and I prime, and I is strictly bigger than I prime, then there is a way to extend I prime to a bigger independent set by including some element which is not in I prime but in I. Right? So in other words, there exists some x in I minus I prime, so that this is also independent. Okay, and actually most of the terminology for matroids comes from linear algebra. So a typical example to keep in mind is that so your universe is a collection of vectors, and independent really means they are independent over some field. And so then you should see that, okay, if some set is independent, that its subset is also independent. And extension property also holds, right? You can always extend a set, add some another linearly independent vector if some set is smaller. Okay. So one big program in matroid theory is to understand how do these matroids look like. Because notice, unlike graph theory where you have some kind of structure, these matroids are defined by properties. So it's not really clear what the structure is. And this is, of course, a whole industry in itself. And so the typical question is how does a random matroid or a typical matroid look? And there has also been attempts to define a certain notion of random matroid theory. And again, it's much less developed than a random graph theory, for example. And we don't even know very basic questions. And in fact, one of the most basic questions that you can ask, right, is how many matroids are there on n elements? Because if you want to define any kind of probability or something, you better be able to at least answer this. And notice one trivial bound is, of course, 2 to the 2 to the n, because you have n elements, so you can have up to 2 to the n subsets, and it's any collection of subsets. Right? So yeah, this is the trivial upper bound. Now already in 74, I guess it's almost 40 years ago, Knuth showed the following lower bound, that the number of matroids is at least 2 to this number. So it's 1 over n times the central binomial coefficient. And since n choose n over 2 is roughly 2 to the n over root n, so this is roughly like this, right? And the way he actually did it, and we'll see this proof in a few slides, is he constructed an explicit class of matroids, what are known as sparse paving matroids. And he showed that their number is this much. So let's see, so if you summarize these two things, let's see what's already known. So since we'll be dealing with such big numbers, it's useful to look at these things on the log-log scale. So we'll look at log-log number of matroids. Yeah, so this result tells it's between n minus 3/2 log n minus some constants, and this after taking log-log will become n, right? So the number lies somewhere here. Now you might ask, okay, why do we bother about this tiny 3/2 log n? I mean, usually in approximation you just care about constants. So this is negligible. So it depends. I mean, you can give several answers. So one thing is this log-log scale is a bit deceptive, right? I mean, because even if you have x versus x square, once you take the log-log scale, it just translates to an additive 1 error between x and x square. And the sort of more important reason is that it has been widely conjectured in matroid literature that actually most matroids are sparse paving. So people believe that Knuth's lower bound is actually the right answer for the number of matroids, and sort of there are various quantitative versions of what that means, but I won't give you bother you with the precise conjectures. There are several of them. Yeah, but morally they mean that Knuth's bound is sort of close to the right answer. Okay, good. So just recall Knuth had this 3/2 log n, right? Now we saw an naive upper bound of 2 to the 2 to the n. Notice it can be trivially improved, and we can shave off this half log n as follows by just looking at basically matroids of a given rank. Okay, so again, what is the rank of a matroid? So recall, because of this, again we all know this. So the maximal independent set in a matroid is called a basis, and all of them have the same size, right? Because of this exchange property. If they did not, then you could extend one of them. And the size, so the size of each base is kind of unique, and it's called the rank of a matroid. Okay, and one way to specify a matroid is of rank R is I just tell you which sets of size R are the bases, right? Because if I tell you that, you know everything else, because every subset of that is a independent set, and every other R set is not a base, right? Okay, so this tells you that the number of matroids on n elements and of rank R is at most this, right? So good. So if you take log of this, you will get log of, so we have first log shaves of this 2, then you take log of this, and this is maximized when R is n over 2, which is like n over 2 to the n over root n, right? So if you take the log, it's like n minus half log n. Good. So, okay, so this is for a matroid of particular rank, and now notice that the total number of matroids is just like at most n plus 1 times matroids of a given rank, and like this n plus 1 is a negligible factor, right? Once you take 2 logs, it like disappears, I don't know, like badly. Okay, good. So this shows that the log of mn is at most this, and this also tells like, okay, so to bound mn, we can essentially focus on the number of matroids of a given rank. Like we don't have to worry, it's just going to add another n plus 1 factor. Okay, so this was a trivial way to get this half log n improvement, and again, like almost 40 years ago, Piff had a little bit stronger upper bound where he could shave off another half log n, so he could show n minus log n plus order 1. So again, Knuth had 3/2, and this was log n, and this was sort of the best state of affairs until now. And so what do we show? So we tighten this upper bound and show that basically, we can recover sort of Knuth's lower bound up to this additive term. And in fact, more precisely, our additive term is just 1 plus order 1. So basically what we show is like log mn is what Knuth had plus 1 plus little of 1, as opposed to Piff's half log n gap. On if you remove the logs, more precisely it looks like this. So Knuth had this lower bound, and we have like a factor 2 extra here, right, which translates to the plus 1 when you take 2 logs. Okay. And the interesting thing is that to prove this, we actually don't need to know much about matroids. In fact, like I'm not really a matroid guy, so sort of very, very basic facts. And in fact, for like almost 90% of the talks, we'll not even talk of matroids, we'll just talk about sort of independent sets in a graph or stables. So I'll actually call these stable sets using the OR terminology, because independent like in matroid means something else, but I might confuse myself anyway, because we are usually used to calling these independent sets, but so this will be our main tool.
So which one? So you expect the 2 to be smaller in the real thing?
Yeah, so
what
that's
is conjectured or what is believed?
Okay, so I'll actually describe exactly, So it's believed that the number of matroids is close to what are called sparse paving matroids, which is the class Knuth constructed. But presumably, like sparse paving matroids could be more than this. So one doesn't know, right? Like there could be a gap both.
So you believe essentially all matroids were sparse paving matroids?
So I don't know much about matroid, but
But
Matroid theories.
I mean, is
Yeah.
there any counterexample? Now you do. Include matroid as a sparse.
Yeah, you can give definitely. Like sparse paving is a special class. We'll see actually what they mean. It's a very, very special class, but somehow so you can like spanning tree matroid, for example, is not sparse paving, right? But the point is these are like very tiny fraction of this huge space of
It's very
matroids.
hard to construct one, but almost everything.
Yeah, exactly. In fact, like, the most explicit examples we know are not sparse paving matroids, but yeah. But we'll see what these are in a moment and it'll be clear. Okay. Okay, so the outline of the talk will be roughly the following. So first I'll tell you this Knuth's lower bound construction and what are these sparse paving matroids. And then for a while I'll talk about sort of some technology to count the number of stable sets in a graph, and then we'll see how this connects to matroids in the end. Okay. So next couple of slides I'll tell you how Knuth came up with his lower bound on the number of matroids. Okay, so the first observation is if you want to specify a matroid of rank R, you could also just specify the sets of size R, and I'll call these R sets, which are non-bases, right? Because if you tell me which sets of size R are non-bases, so the other sets of size R are the bases, and all of their subsets are independent sets. So this will give you entire everything you need to know about a matroid. So it's like a complete description, and it's convenient to define the Johnson graph, which again probably many of you know. So this graph has two parameters n and r, and it has n choose r vertices corresponding to each subset of size r on these n elements, and you put an edge between these two vertices if they basically are common on r minus 1 elements, right? So I think I have a picture. Yeah. So in other words, yeah, like, so these are two sets of size r, and if they just differ in like one element, then there is an edge between them. So a more convenient way to think of them is like you have a 0, 1 vector of n dimensions where you have exactly r ones, and there is an edge between two vectors u and v if they, you make a 1 to 0 and a 0 to 1 somewhere else, right? So you just swap. Now notice one thing, it's a very structured graph. So one thing is like it's a regular graph with degree r times n minus r, and why is that? Because yeah, how do you get to a neighbor? You make one of these ones to a 0. So there are r choices, and where there was a 0, you put a 1, right? That's a swap. So there are r times n minus r options. So see? Okay. Now here is actually a very simple theorem. It's very easy to prove. So it says the following. So if you pick any stable set in this Johnson graph, or in other words, you pick these r subsets which don't differ by one swap, right? So there is no edge between them. So pick any sort of stable set in this Johnson graph, and if you call those as your non-bases, then that gives you a matroid. Okay, so is the...
Where basically you're saying bases define a matroid, or non-bases define a matroid as well.
Yeah. So if I just pick some stable set in the Johnson graph, those are my non-bases. Every other vertex in this Johnson graph is a basis, and that will have, that will always form a matroid. And actually, for those of you who know what base exchange property is, it's very easy to see. Because the point is, like, whenever you have two bases, you won't get blocked, you can always find a path. But again, if you don't know what base exchange is, it's, don't worry about it. It's like a one-line proof though. So, but we can take this result on faith. Yeah, and these are precisely called the sparse paving matroids. Okay, so this class, and again there are sort of various other characterizations of this, but this is one useful way to think about it for our purposes. Okay, and these are extensively studied also, like in matroid theory.
Is this like stable set is the right property, or do you want some kind of a cut kind of a? Because as you said, right, you want a path from between two.
Okay, good. So stable set is sufficient because, right, so what could go wrong if it's not a matroid? If you take two bases, you can't find a path, right? And what is a path? You try to like do a one swap, right? So if you can't, okay, so suppose I just take two bases which differ in two elements. Like if it's just one swap, there is a trivial path. So let's say they differ in two elements. But then if I can't find a path this way and I can't find a path this way, then these both guys are non-bases because they are both blocking me. But then there is an edge between them, right? So it's just that, right? Yeah, so it's sufficient. I mean, of course there are other matroids which do not satisfy this, but yeah, that's the whole proof. Yeah. So again, a stable set is always a matroid, but of course it's not if and only if.
This is even only for sparse paving, right?
Yeah. So that's the definition of sparse paving, like one definition of sparse paving. Yeah. Yeah, there are also various other characterization in terms of dual matroids and all, but okay. But this is yeah. But again, as I said, we'll just mostly talk of stable sets, right? Okay. So yeah, as I said, sparse paving matroids are precisely the stable sets of this Johnson graph. Right. So let's look at these for a while, and we are doing the Knuth's lower bound. So one thing is, let me denote, given a graph G, alpha G as the size of the maximum stable set, and I'm interested in the number of stable sets of a graph, right? Let's call it Ig. So clearly, Ig is at least 2 to the alpha G, because if you have an independent set of alpha G, every subset is an independent set. So what does this give us? Right, and again, because we want to, so one way to lower bound the number of matroids is to show lower bound the number of sparse paving matroids. So that's what we are going to do. So let's see what this naive, yeah. So if you can lower bound alpha G, then you have a good lower bound on number of independent sets using this. So already, yeah. So one trivial lower bound is just the following. So we saw this Johnson graph J and R is regular with degree R times n minus R. Right, because it's one swap neighborhood, and when R is like n over 2, it's roughly n square over 4, and we know that any deregular graph has an independent set of size at least n over d plus 1, just the greedy algorithm will give you. So this, yeah, so this Johnson graph with R is n over 2 has these many vertices, and the degree is roughly n square over 4, so it will give you something like 2 to the n over n to the 2.5. Right? So yeah, so that's alpha G, and so Ig is at least 2 to the 2 to the dot. So that's like a trivial lower bound, and what Knuth did to show, he showed actually the alpha G is at least 1 over n instead of this 1 over n square, 4 over n square thing here. And the way he did it was actually just to give a very explicit coloring, n coloring of the Johnson graph, right? And actually this coloring is very sort of cute, so, and it's very simple to describe. So again, a vertex in the Johnson graph was just 0, 1 vector with R1s, right? So associate the following number with a vertex V, like, so you look at the ith coefficient multiplied by I and then sum over all the coefficients, so IVI. Now, yeah, so let's focus on this number. Now I claim that if you have two neighboring vertices, this number can differ by at most n between these two vertices, right? Because what is a swap, right? You drop something and you add something, and these coefficients are always between 1 and n. So if I look at this number modulo n, all neighbors will be colored, yeah. So for any edge, like no two, both the endpoints will be colored with different guys, right? Yes, yeah. Right. So it's a very simple explicit coloring. So it tells you that the independent set is at least this. Now one thing, actually I'll also tell this in the end. So presumably it could be, the maximum independent set could be bigger, right? But nobody knows of an other lower way to lower bound it. So that's sort of one trouble. So if one could push this somehow maybe to 2 over n, for example, then actually it would give a tight result, right? Like I haven't told you the upper bound proof, but because we also prove an upper bound of like 2 to the 2 over n times n choose n over 2.
Current number is n. There's a clique for size n or something?
So that's not, no, so that's not clear actually. And there are for small values, so people have done experiments and there seems to be like 1.3 or something. Yeah, so there is no.
This is for the independent set. I'm just asking about coloring number.
Okay. Yeah, that might be, okay, I haven't. Yeah, I'm not sure. Yeah. Yeah, there is at least a clique of size n over 2. I don't know about n, but yeah. Okay. Good. Okay, so any questions so far? Because that proves the lower bound, right? So if the alpha is at least this, then the number of stable sets is at least that, and each stable set is a sparse paving matroid. Okay, so that was the whole lower bound. So now we'll sort of come to our upper bound. So again, recall our goal was to show this upper bound that the number of log number of matroids is at least Knuth's lower bound plus 1 plus order 1. So actually, when we first started thinking about this problem, the first idea was, okay, if you want to upper bound the number of all matroids, you better be able to at least upper bound the number of sparse paving matroids by something that's close to Knuth. If you can't even do sparse paving, there's no hope you can upper bound everything. And yeah, so that's the step we focused on. And this was actually nice because this is like a very clean object, right? It's just the number of stable sets in the Johnson graph, so it's a purely combinatorial problem. And luckily, like the ideas we developed here turned out to be directly extending to matroids, which was kind of fortunate. Yeah, so sort of most of the talk I'll just talk about, yeah, so I'll denote Sn as the number of sparse paving matroids and how to bound this, yeah, and then there'll be the extension to matroids. Okay, good. So yeah, so we'll try to upper bound the number of sparse paving matroids. Okay, so the first claim we'll use is the following, that the maximum stable set in the Johnson graph is at most 2 over n times the number of vertices. So I'll denote it by capital N, this n choose n over 2 instead of writing every time the number of vertices. And notice Knuth already showed that the lower bound of 1 over n times n, and now we are saying that, okay, the upper bound on the maximum independent set is at most twice of that. Okay, and actually this follows from what's known as Hoffman's bound, and probably many of you know, which just says the following. So if you look at the adjacency matrix of a graph, and if minus lambda is the smallest eigenvalue, so again smallest eigenvalue will always be negative because eigenvalues sum up to 0, then this lambda n over degree plus lambda is a upper bound on the size of any independent set. And actually we'll see a proof of this in a couple of lines, and probably many of you have seen this before. Okay, now for the Johnson graph, this spectrum is sort of very well understood. They are very widely studied graphs in sort of algebraic graph theory. Yeah, and it's known that, so we saw the degrees like n square over 4, and it's known that the smallest eigenvalue is like minus n over 2, so lambda is n over 2 in our terminology. And if you just plug these numbers here, you will get this upper bound. Okay, okay, good. So we can upper bound alpha g by this. Now let's see what this gives us, right, like on the number of, or at least naively. So if you know that the maximum stable set in your graph was alpha g, then the total number of stable sets cannot be, it's either n choose 0 plus n choose 1 or all possible subsets up to this, right? And so in our case, like alpha g is say bounded by this 2 over n times n, and so this term will sort of dominate, so it will roughly look like this. And if you just look or use Stirling's approximation or whatever, or the binomial approximation, it will give you some constant n, which is the ratio of n over k, right, to the 2n over n, right. Okay, so this is like a naive way, just using Hoffman's bound together with a naive enumeration gives you this. Okay, and what lower bound did we have? It was 2 to the alpha g. So notice there are two things that differ between this upper bound and lower bound. So one is the base of the exponent here, and that's the crucial. So here it was 2, here it's like n, and then there is this factor 2 sitting here also, which we won't be able to remove because, yeah, that's the best upper bound we know on the stable set. But yeah, this n is sort of problematic, right? Like because if you take n, it will become log n in the exponent here, which is not quite what we want, right? So the point is, yeah, this naive way of counting independent sets, number of independent sets, is kind of lossy. So what we will show actually that, okay, let me go back. So instead of n to the 2n over n, the number of independent sets in the Johnson graph is actually 2 to the twice n over n. Okay, so we can shave off this base from n to 2 down. And morally, you should think of this bound as saying that most independent sets in your Johnson graph are subsets of this one large independent set, right? Because, right, it's not like they are smeared out everywhere, but yeah. So actually, this phenomena happens more often, all around us. So the most sort of natural example is to look at the hypercube. So say you have a n-dimensional hypercube with 2 to the n vertices. Let's call it capital N. Then it's a bipartite graph. So we know that alpha g is n over 2. So again, what the naive way of counting all possible subsets of size up to n over 2 would give you the following upper bound on the number of independent sets, right, which is like almost half of 2 to the n. It's pretty much useless. Now, what's the right answer? And actually for hypercube, people have nailed it down exactly like to constants. It's quite an amazing result. So the right answer for the hypercube, for instance, instead of 2 to the n, it's like 2 to the n over 2. Yeah, so again, you should think of, and in fact, this is a very small constant, right, like 3 or something. So what this is saying is that Yeah, so there are, in the hypercube there are these two independent sets of size n over 2, n over 2, and essentially every independent set is coming from one of these guys, right? Yeah, so maybe this is the right picture. So hypercube is, yeah, this graph, and essentially everything either comes from here or here. And intuitively this makes sense for the hypercube, right? Because point is, the moment you try to pick a few vertices here, it will sort of block a lot of vertices in your independent set on the other side. So if you want to pick really lots of independent sets, you better just stick to one piece. And this will be sort of the idea that we'll try to use. And this example already tells you that to be able to do this, you have to, so the reason why this is happening is because of the expansion in the graph, right? Like if you try to use something from here, it blocks a lot of stuff here. And somehow your bound should take into account expansion. So otherwise, yeah, if you do something naive, it won't be strong enough to do it. Yeah, good. And as I said, like, yeah, this kind of phenomena happens more often. So in fact, there is a very interesting result of Jeff Kahn, which says that for any deregular bipartite graph, like not just hypercube or whatever, so the independent set is at most 2 to the n over 2 plus n over 2d. So again, this 2 to the n over 2 is the right thing, which morally says that most independent sets come from one piece. And actually what's nice about this result is it's exactly tight, because if you have say n over 2d copies of this kdd complete bipartite on d by d, so there are n vertices, right? So this graph has 2d vertices and I take n over 2d copies, so it looks like this. Then for each of these pieces there are 2 to the d plus 1 choices for my stable set, right? Either I can pick any subset here or any subset here. And then if I raise this number to the n over 2d, I'll get exactly that. So this is like, yeah, exactly correct. And there was a nice result of Zhao recently which showed that this even holds for general graphs.
And d in that case is what? The general graph?
D is the degree.
The average degree or?
Okay, so he proved, so Jeff Kahn proved it for deregular, but maybe these ideas
For
extend.
general graphs.
Okay, so they're also general deregular, but not necessarily bipartite.
Okay.
Yeah, but I think there might be a simple argument which shows that these are extremal cases when it's regular, or you can do some swapping argument and make it regular, I think. Okay. Okay, so what do we show? So our result is another bound on the number of independent sets. And it's, okay, so if you have any deregular graph with minimum value minus, eigenvalue minus lambda, then we can bound the number of independent sets by, so let's ignore this term for now, this is the main term. So recall this was the Hoffman's bound, right, the size of the largest independent set. So basically we say it's 2 to the alpha g, so essentially everything is coming from just this guy. And this is supposed to be like a negligible term, it's like, yeah, 2 to the n over d roughly with some log square factor sticking in, okay. Okay, and what, yeah, and notice it's not such a bad bound, because if we look at say the setting where of a bipartite graph, like any arbitrary bipartite graph, then we know that the smallest eigenvalue is minus d, right, corresponding to this eigenvector. Okay, so lambda is d, so if you plug it in our bound, this will become like 2 to the n over 2, because lambda is d, so this is half. Yeah, so they'll give you 2 to the n over 2 plus this small term, right? So Kahn's argument, he had plus n over 2d, and so we lose this extra log square additive, but we sort of get the dominating term, right? And actually this also holds for, so this holds for any general graph, right? And so this proves also this bound for a general graph, because lambda again is only minus d or higher. Sorry?
Zhao result for any deregular graph.
Yeah. So my point is like, so we'll give a much more general argument in terms of lambdas. So why is this useful? Because if your eigenvalue was smaller, it was away from minus d, then this gives you a much tighter bound, right? Because for our Johnson graph, we don't want something like n over 2. We wanted something like this capital N over small n, right? And that's the whole, yeah. So we cannot use off the shelf Zhao's bound or whatever. We, yeah. So my point is like this theorem kind of essentially recovers close to these Kahn and all, which was a long line of work, but also is sort of much more general. Okay, Yeah. So this is, I'll try to give you a flavor of this result in the next couple of slides. Okay, so the whole idea of this proof will be, given an independent set, we'll give some kind of an encoding scheme. So it's like a computer sciencey way of counting. So we'll show that you can always encode an independent set using a few number of bits. So it cannot be more than 2 to the number of bits that you use. Okay, and this approach is sort of, again, there has been a long line of work in this work starting from Kleitman in the 60s, but our approach is sort of closest in spirit to a recent paper of Alon et al. But sort of the bounds they get are weaker and were not useful for our purposes. And also, as I mentioned earlier, this encoding idea that we'll develop for stable sets will be useful for matroids. Okay, so the rest of the talk will be, I'll describe these two things. Okay, and before I give the proof, so here is a useful lemma which is useful by itself, I think also, which says the following. So suppose you have a d-regular graph with minimum eigenvalue minus lambda, then the following holds. If you look at any subset of vertices, call it A, then the number of edges within A, right? So let me denote G of A as the graph induced on this A. So the number of edges is at least this number. And again, so this is sort of the dominant term. And so what this means, like suppose now you looked at a random subset of vertices, capital A.
LHS is the number of edges within A.
E of G of A. Yeah. Yeah, so G of A is the graph induced on A and E is just the number of edges. So it says that, yeah, no matter which subset of vertices you pick, the number of edges is at least something. So it's giving a lower bound. And how do we, the right way to think about this lower bound? So suppose you picked some random set A in your graph, right? So let's say this was a random graph. Now, if you look at a typical vertex, you'll expect a degree of, so it has degree D in the original graph. So, and you are picking A as a random set. So you'll expect its degree to be roughly like this, right? A over n fraction of its neighbors will be here. Yeah, and you are picking A such vertices. So the total sum of degrees will be this in expectation, right? And that's twice number of edges. So basically what this theorem is saying is that, yeah, twice the number of edges or the sum of degrees is essentially what you would expect for a random set minus sort of some error term which depends on how your minimum eigenvalue looks like. So if this was say much smaller than compared to D, then you would, then every set behaves like a random set. Okay, and this actually, sorry, yeah, so let me rewrite this again. Okay, and how do we prove this? Again, it's a standard result, but it's sort of, you do the usual thing that you do, right? Like, so you want to find the number of edges in A. So if G denotes the adjacency matrix of this graph, then it's nothing but, you just sum up over all these pairs. This will count exactly what you want. And this you can write it as this, where chi is the incidence matrix of A. And then you do the usual thing, you expand this chi A in terms of the eigenbasis of G, right? And we know that the largest, so one of the eigenvectors is 1, 1, 1, 1, 1. So I write this chi A as A over n times 1, 1, 1 plus other vectors which are orthogonal to this one vector. So this is removing the bias. And sort of I expand out to the usual thing and the thing pops out, right? So again, probably many of you have used these arguments. So I don't need to elaborate. Okay, so one corollary of this is just Hoffman bound just pops directly because, right? Because if your set A is independent, then the number of edges within it should be 0. So you just ask like, what's the largest A I can push so that this stays 0? And if you just do the algebra, it will come out to be this. Okay, good. Okay, so the useful corollary of this result for our purposes will be the following. If I look at any set A of size say epsilon L, where epsilon is some small constant, plus some little term that depends on the spectrum, think of this as a negligible term because lambda is much smaller for us than D, then essentially, yeah, so what this theorem says is that this guy will have a lot of edges, right? This set will behave like a random set of size epsilon n. So in other words, then GA has a vertex of degree at least epsilon D. So this will be a useful corollary of us. Okay, so here is based on this how we do the encoding. And again, the idea will be in this slide I describe the idea. So suppose, so again, there is some stable set I in our graph. I want to encode it somehow. So one way to encode is just to write it down exactly, right? This vertex, but so that will exactly give you the naive bound that we had, because the size could be up to alpha g and you write log n bits for each of them. Okay, but here is a potentially more useful way to do this. So maybe this picture is useful. It's not the most accurate, most exact picture, but it's a useful analogy. So suppose there was this independent set that you would like to encode using a few number of bits. Now, if you could do the following, suppose you could find a small set S. So this S is supposed to be like very tiny, right? And formally think of it as this size. So this set S is contained in my independent set. Suppose I could find such a set. But this set had a large neighborhood, like a very, very large neighborhood. Suppose I could do that. Then you know that your independent set must lie in this remaining region, right? Because this set S rules out all of this red part, like this cannot lie in your stable set. So for these remaining guys in A, I just need to say, like need to use one bit 0 or 1, whether it's in my independent set or not, right? Or in other words, this independent set is completely specified if I could find this sort of seed set, and in the remainder, which of these guys lies in my A. Okay, so the number of possibilities for I is, so if we could give such an encoding, it's n choose S, because for all possible ways of choosing the set. But once I choose my set, it fixes my A, and then I only need to specify 2 to the A, need like 2 to the A combinations, right? Like which subset of that is there. Okay, so this so this will be the idea, to come up with an encoding scheme which specify these properties, and if you just plug these bounds for S and A in this recovers exactly your result. Okay, so why should such an encoding scheme exist? So let me sort of try to give a sense, almost an exact proof. Okay, so here is a way to encode the independent set. So initially we set, so there is some independent set given by these red vertices that I want to encode, right? And I just don't want to list all these vertices, that's too many bits. So I'll do the following. I'll start with all my vertices, and let's say I'll arrange them in the order of decreasing degree. So this is the maximum degree, the next one, and so on. And ties I break in some like fixed order. And let's consider the following procedure. So I look at the first vertex, and maybe I have an animation for this. So if it's not in my independent set, like this blue one, I just discard it. And so the first guy is not in my independent set, I discard it. Second one I discard. Now this guy is in my independent set, so I choose it, and if I choose this guy, it rules out a lot of other guys from being right, all its neighbors, like in the remainder it will rule out. Okay, so I keep doing this. Okay, so now these guys are ruled out, so I remove them. Now in this remainder graph, maybe the ordering of the vertices changes because it's by degree, and then I keep continuing this procedure, okay, until my remainder vertices are this Hoffman's bound on the independent set, because then I can't guarantee you any edge anymore, right? Maybe it's stable set, so the procedure sort of doesn't kill any vertices when I pick something. Okay, so the whole crucial observation is that so at the end of the day, right, when I'm left with so many vertices, I have picked some vertices like S. So one thing is that this S that I have picked, like these red vertices, it completely determines which set is left over. Why? Because this was a completely deterministic procedure, right? So for example, like if you go in the very beginning, right, so in the beginning, like you knew what was the ordering on the vertices. Now at the end of the day, you are left with some set S. You see, oh, the earliest vertex in my set S is this in this ordering, so I must have rejected these two, right? So, and you keep applying this argument. So if I tell you this set S, it exactly tells you what's your remainder set at the end of the day, right? Huh? Kind of, yeah. Yeah, so this is just a small seed that sort of determines what's left over. Yeah, you can think of it. Good. And there is just some calculation to show that, okay, and what's the property, right? So the point is that initially if we pick some vertices, then we had arranged these guys in the order of degrees, right? And we had this argument that if I look at, say, some big set, then large sets have a lot of edges between them, right? This was that lower bound, that spectral lower bound. So it means the highest vertex should kill a lot of vertices there if I pick. So you can sort of do some math and show that because of that, the number of vertices that you pick up cannot be too much, because every time you pick something, you kill a lot of guys, and you can only kill so much. Okay, and so that basically tells you that the set S that you pick is roughly like log d over d times the number of vertices. Okay, so just to recap, maybe it was a bit quick. The idea was, again, like you want to encode some independent set here, you find a subset S which sort of rules out a lot of things, and this set itself is not too large, and so your independent set can only be in this region, and this A is also completely determined by this set S, so you only need like a 0 or 1 indicator and not the whole log n bits. Okay, good. Alright, so this was the part for how to capture independent sets. Now how do we encode, how do we extend it to matroids? Because now we are trying to count general matroids, right? Not just sparse paving matroids. So these are not necessarily independent sets. I mean, they could have non-bases, could be all spread all over the place. Okay, so we'll use one more idea, but the main idea will be the following. So again, a matroid could be specified by saying which of the R sets were non-bases, but I'll efficiently encode these bases instead of listing like each one out there. And again, the picture to keep in mind is that, right. So if I'll find a small set S, okay, and again, like if I think of the Johnson graph, maybe these are all the neighbors of this graph. So in the previous setting, I could say in my independent set, none of this can lie, and my independent set can only lie here. But now, because we don't have independent set, maybe you also include some guys from here as your non-bases, right? That's the whole complication. But what we'll show, so this is the next key lemma for matroids, that all the non-bases in this neighborhood of S can actually be specified by essentially twice the size of this guy. Okay, and it'll be clear what I mean by this. So even though your matroid could have lots of guys here, lots of guys as non-bases here, you could just there is a very small sort of witness for them. And let me explain you what I mean by this. Okay, so once I prove this lemma, the encoding is clear, right? So because I just store my set S and the non-bases in A like previously, and the only difference here is that for the non-bases in this neighborhood, it could be many, but I'll just have a very small witness which will tell me which ones. So the total number of bits I use is not too much. I just have 3 times S log n bits plus 0, 1 bits for this. Okay, now what do I mean? So what's the idea that, right, so what do we want to show is that, lots of non-bases here can be specified by a few number of sets, and the idea will be the following. If I look at any set and I look at its neighborhood, right, in the Johnson graph, there are these n square over 4 guys, and maybe lots of these vertices are also non-bases, right? But instead of, so one way to specify them is to list each of them, but we can actually give a very concrete representation. So instead of listing all of these which are non-bases, I'll just describe 2 sets which will encode which of them are non-bases, and the reason is, and this is the following structural property, that so if X is a non-base, it's R set which is the non-base, and there are many other non-bases in NX, then there is some kind of underlying reason for these guys to be non-bases. So let's look at the following example, right? So say you have a graph and your matroid is the spanning tree matroid. Okay, so a set like this is a non-base because it has this circuit. Now look at the possible neighbors of this guy, right? So a neighbor was just when you flip one thing and add something. So this is a neighbor, this is a neighbor. You'll also have other neighbors where you break this cycle and add some other edge. Okay, but for all but there can be several neighbors like this, right? Now, for all these neighbors, I can just list the reason that, oh, there is this cycle there, and that's why they are all this. So instead of specifying each of them using a lot of bits, I can just say, oh, here is a cycle, and anything that contains its cycle is like, yeah, so there is a very concrete, just this one cycle, which tells you the whole information instead of storing everything. So this is sort of the intuitive idea that, yeah, there is like inherent reason why things in the neighborhood of something are non-bases. Okay. Okay. So here is a way to make this whole thing imprecise, and again, it's a little. So this is the only place where we use some properties of matroids, but it's just this one slide. So let me go over it in case those of you are more familiar with matroid. So the key lemma is the following. So if you have a dependent R set X, or it's a non-base, then we can associate two sets that are witnesses for all the non-bases in the neighborhood of X. Yeah, so instead of, like, there could be up to n square over 4 non-bases, but I'll just exhibit two sets which give you all of a witness. Okay, so here is the whole proof of this. Okay, so look at some neighbor y of X. It means that y is of this form where you throw some element X from this and add some element Y. And let's look at two cases. Okay, yeah, so this is case one. So suppose your X to begin with, it was a dependent set, right? So it cannot have rank R. Suppose its rank was R minus 2 or smaller. Then actually I can just take my witness as this set X, because what is Y? It's just you're adding at most one element to X, so it can't have rank more than. So this is just a very concrete witness for such guys, right? Everything in the neighborhood is dependent. So this is a trivial case. So the more interesting case is when your X has size R, rank R minus 1. Okay. Now in that case, recall the basic property that X will have a unit circuit, right? Like spanning trees may be the easiest. So there is one unique cycle. And what I'll show in a sec, so the witness we'll associate with this X is this unique cycle and what's called the closure of X. And the closure of a set is just if I add all those extra elements which don't increase the rank of X, that's the closure. Okay, so why is this witness enough? So here is the proof. So here suppose there are two sets X and Y which are non-bases, and Y is obtained is a neighbor of X, so it looks like this. Then first claim is, and again this is just a one line calculation that I'll skip, that so this was a non-base of rank R minus 1 and Y is also a dependent set. So either it must be that when you remove this element X from X, its rank fell down to R minus 2, and even when you added up it could not go all the way up to R, or it could be that, or it must be that X plus Y has rank R minus 1. Yeah, so this can only have less rank, and you can show that, yeah, just by submodularity that either of these cases must hold. Good. Good. So if rank of X plus Y is R minus 1, this means X lies in the closure of Y lies in the closure of X, right? Because X had rank R minus 1. So if I give you this as a witness, then everything that is in that closure of X tells you, yeah, just this one set tells you all these other sets that will be expanding. And if rank of X minus X was R minus 2, yeah, and notice R minus 2 is strictly less than the cardinality of X minus X, right? Because this was cardinality R, so this is R minus 1. So it means X minus X must contain some circuit, but that circuit also lies in X, right? And but X only has a unique circuit because it was of rank R minus 1. Yeah. So if I just specify this circuit I, that tells you, I mean, that's the reason why your rank is R minus 2. So if you add any Y, it will still increase. So that's basically it, right? So yeah, for each guy I can give a concrete thing. Yeah, so just to maybe recap, we kind of do essentially what we did in the stable set procedure, but instead of, yeah, we find these sets S and A, but now we also store witnesses of the neighborhood in each X, which is not too large. And that gives the efficient encoding. Okay, so just to conclude, so we showed this gap, yeah, so we showed this like much stronger upper bound on the number of matroids, but we still have this 1 plus order 1 gap, right? It would be nice if it can be reduced to little o of 1, but there is sort of an inherent bottleneck, at least why this approach fails. And probably why maybe any approach based on sparse paving matroids would fail. And the reason is that we don't quite understand how the max stable set in this Johnson graph looks, right? This is what Mohit was asking. Because again, Knuth gave this explicit construction of this much size, and the best way we can upper bound is only this. And as long as this remains, you'll always have 2 to the alpha g. This 2 will stick up in your exponent and won't go away when you take logs. It'll give that 1 plus O of 1, no matter how clever you are on the other things. So sort of one natural way to break this gap would be, to understand what really is the truth. And actually this question but this might be a hard question, I think, because this actually problem of stable sets in the Johnson graph, there are lots of papers in the coding literature, and people have also done like simulations of up to n is 24 or something. I mean, this is already a humongous graph, so they use a lot of symmetries and all kinds of things. And the simulations seem to suggest the answer is like closer to this, but it's hard to judge because it's something like 1.07 n over n up to 1.3, and presumably it's converging to n over n. Who knows, right? These are small numbers. But yeah, so if this is the right answer, then presumably, okay. So maybe even if this is the right answer, one problem is we don't know of any other general techniques to upper bound stable set other than sort of these eigenvalue methods, or there is Delsart's method, which is also sort of similar. But maybe one could use stronger Lasserre hierarchies or something to upper bound it. I mean, that's the only technique I know. And perhaps if we got a method for certifying that upper bound was actually this, then maybe one could on top of it combine with matroid techniques to actually do the same machinery that we did and get the right bound on Mn. But that's probably it's a long program. Okay, so that's it, and thank you for your attention.
Can you go back?
Yeah.
So this would imply the number of independent sets, bounded number of independent sets as well?
Yeah, so assuming, okay, so again, who knows how this machinery will look, but you would have to kind of carry it out, right? Because for us, we use the Hoffman's bound, right, with 2 n over n, and then on top we built all this eigenvalue, to actually show that most independent sets come from just this guy, right? It's not like n choose this, but more like 2 to the n over n.
But did you ever use the structure of this thing? Right? Did you?
So we used eigenvalue arguments in that, right, to show such a thing. So this was the right, but hopefully, so that would be one piece one has to do.
No, but exactly where did you? Oh, so okay, this is
all
the
this,
case. This was the case.
exactly, right. And actually the theorem we can show is only this, and the reason why this is good is because this is like 2 to the alpha g. But maybe if one tightened this, it's not clear whether this technology to push that, but presumably it should if that's the right thing. But it's not a black box reduction. Anything else?
More questions?
Have people looked at the theta function of this?
Yeah, so theta function is exactly gives you Hoffman bound. Yeah, so there is a paper from Scriber back in the 70s, all these things. Yeah, so all these things, Delsart's method, theta function, and eigenvalues, they are apparently all the same. I don't quite understand why, but yeah. So.
Let's take this again.